We've got to go through 15 horsepower comparisons and then put it all back together for a final recap of what we've done. So this is our 383 V8 operating on 4 cylinders and producing 15 horsepower at 1,085 RPM. This is the as-supplied cam with 45 degrees valve overlap. Here it shows the duration at 3 thousandths lift at 266 intake and 272 exhaust, and the duration of 210 and 215 at 50 thousandths lift. The dynamic compression ratio is 7.53, and the closing events for intake is 67, and the closing event for opening event for exhaust is 67. So it has the same compression ratio as it has expansion ratio. So we're going to do a little bit of valve overlap analysis at this load setting to see what kind of numbers it gives us. So this is the C engine feature, and you can see that right now the piston is coming up towards top dead center and is at 324 degrees. Now right over here we have the exhaust pressure in PSI and exhaust velocity is currently exhausting at 91 probably feet per second. And over here is the pressure and velocity on the intake port, which the valve is still closed, so it's not doing anything at all. We come in here and we move it. Now we're at 328. Now we're at 332. And now we're at 336. 340, that's 20 degrees before top dead center. And 344, and notice that we now have 1 negative velocity. At 348, we have 1 negative velocity. At 352, the negative velocity is 7. You can see the arrows here clearly pointing which way everything is moving. We have negative velocity of 18, and now this arrow has reversed direction. There at 360, we've got a negative intake velocity of 29, and then a negative intake velocity of 40 at 364. That's 4 degrees after top dead center. At 68, our negative end velocity is 39. And now it's down to 15 at 372. And when you go to 376, there is 0 negative velocity, and now we have a positive velocity. If you add all these negative intake velocities up, you end up with negative 150, and we can compare that to the custom cam that I put together and see how it fares. So here we have the 383 V8 operating as a 4-cylinder with the custom cam installed, and notice that we have 24 degrees of valve overlap as opposed to 45. We're pretty close to our dynamic compression ratio is 7.54. And if you look at the intake closing at 67 and the exhaust valve opening at 45, you can see that there's a difference there in the exhaust and intake valve opening. So here we have our C engine feature for this set of data, and we're 20 degrees before top dead center, and we'll just move forward and forward and forward and forward. 356. Now we don't get any negative intake velocity until 360. Then we have 1, minus 1. We have minus 7. Then we have minus 13. Then we have minus 1 again. And now we're back to a positive. Now, there's a lot less time for negatives, and the total negatives add up to 22. So when you compare that to how much negative exhaust flow you have to the as-supplied cam at this power level, we've cut that by 6.8 times. And so we're only pumping in 14.67% of what we were before. So we got a lot less exhaust and intake mixing. So here is tabular data, piston position per degree. And if you take 67 and add it to 180, which is bottom dead center, you end up with 247. And 247 shows us right here the piston position is 2.871. If you take 45 degrees plus 180, you end up with 225. And at 225, the piston position is 3.353. So this program uses the piston position at valve intake valve closing to determine dynamic compression ratio. But we also know the piston position at exhaust valve opening. So we know when the end of the expansion stroke occurs. So we can use those two numbers to get a ratio, and the ratio happens to be 1.1679. And we multiply that times our dynamic compression of 7.54, and we get 8.806. So we have a little bit more expansion than we have compression, and it's helping to make our engine a little bit more efficient at low RPM. So here we have the 383 operating as a four-cylinder, 15 horsepower Lena Peak with the as-supplied cam, and I've got Richer Peak on the right and Lena Peak on the left. Now, there is legitimate question as to whether or not we can run Lena Peak with so much exhaust dilution into the intake. We'd probably have to richen the mixture. We wouldn't have quite as good of an idle there. And right now, with this cam, we would make 7.2 inches of vacuum, and we would be pulling 15 horsepower. And but we would probably be Richer Peak. So our range would be right around 490, and that would be the best range we could get Richer Peak on this machine. Now here we have 15 horsepower, 383 V8 running on 4 cylinders with one float bowl dry. It's got a custom cam, 24 degrees valve overlap. And based on that and the amount of exhaust mixing, I think I can run Lena Peak on this machine. And if that's the case, I could be looking at 610 nautical mile range. But if I run Richer Peak, I'd still be looking at almost 500, 497 and a half. So I believe that this is where the change in the cam really is going to account for something on this engine. Here we're looking at a 7.5 horsepower output at 863 RPM. Again, this is the as-supplied cam, and I do not believe we'll be able to run Lena Peak on it, although I did run the calculations for it. I'm looking at an intake manifold vacuum now is up to 9.4, and total horsepower Lena Peak would be 7.5. I've got the same horsepower Richer Peak, and the Richer Peak range would be 546 miles. Here we have the custom cam on the 7.5 horsepower at 863 RPM. I believe we can run Lena Peak on this engine, so we could run our range up to 731 miles. So this is again where the custom cam should be a better fit for this application than the as-supplied cam. Here I have the as-supplied cam on the engine at 4.3 horsepower at 716 RPM. So I do not believe I can run this engine Lena Peak. I think I'll have too much exhaust to intake mixing for that. So I would have to run Richer Peak, and I'd be around 475 miles of range. Here we have the custom cam, 24 degrees overlap, 4.3 horsepower at 716 RPM. I believe we can run this Lena Peak, but that's questionable. Maybe we can't. But if we can run up to about 779 nautical miles of range versus 420 for Richard Peak. I'm guessing that this engine would run leaner than Richard Peak, even if it didn't make it all the way to 16.65 air-fuel ratio. Okay, so I wanted to look again at the Redfin fuel and air curves for the 383 Marine engine. This is a totally different way of looking at engine horsepower. All we are primarily concerned with is air flow and fuel flow. Airflow as defined by the MR numbers, which line up with the green airflow curves. And then fuel flow, which is defined by these GPH numbers, which line up with the black fuel flow curves. And then across the scale across the bottom is in horsepower or percentage of horsepower. And the scale up the right side is an air-fuel ratio, both in AFR and in Richard Peak versus Lena Peak. In order to determine the horsepower, you start by reading the manifold pressure gauge in the tachometer, and that gives you an MR number. The MR number then gives you a curve to follow, and that curve is vertical in the biggest power band, the high power band of the air-fuel ratio, and then it moves down, the power moves down as you get into the best fuel economy band of the fuel flow meter. So if you are looking at 53.7 right there, and you follow that curve down at 100% power, the leanest you could be at 100% power would be about 11.4. Wait a minute, not 11.4, I'm sorry. 12.4 gallons per hour. The richest would be about 13.7. So that's your power band. And if at the same airflow, on the same curve, you come down here, and your best power is at 50% power. You're a little bit lower on power, but 9.6 gallons per hour, and that gives you the best fuel economy for that range. That's 50 degrees Lena Peak. We also have the Redfin fuel and air curve. I mean, the Redfin stress curve. Now, this Redfin curve is more conservative than perhaps it should be. There's a good argument that this blue dot right here should be the point of this curve. So the blue dot right here could be the point, or the point could be here. I think this would be too much stress on the engine, but I've got the curve more conservative so we can be more conservative in what we're thinking about. So here we have the existing engine on the left and the new Creta engine on the right. This is the engine to replace the existing engine. It should give as good a performance or better, should get better fuel economy, and should get better power, because I designed for about 300 horsepower. Here's our engine as I was installing the new cam and dialing it in to make sure that the timing was as I wanted it. Here I have the carburetor mounted on the intake manifold up in the upper left, and on the right, upper right, I have the exhaust manifolds mounted. Now, I am putting air-fuel ratio sensors here for cylinder number 7 and here for cylinder number 8. And then I'm also putting in exhaust temperature probes in every cylinder so I can verify even fuel mixture distribution between the cylinders. I designed and carved vortex generators into the throttle bores in the spacer plate that the carburetor sits on. The idea is to get the air to swirl as it goes down to the bottom of the plenum of the intake manifold. And then once it turns and goes sideways and goes to the cylinders, it should straighten out. The idea is to get better fuel and air mixing for better air-fuel ratio distribution between the cylinders. I intend to equip this boat with 24-volt house batteries to run a bow thruster and a AC inverter. So I've got 2 charging alternators, and I'm custom building a bracket to put them on. So this is the first mock-up of the bracket in plywood. And here is the bracket built out and mounted in steel with the belt. So should be able to pull all the power I need from the 2 charging alternators, even at low idle. The charging alternators, the 12-volt alternator is 95 amps, and the 24-volt alternator is 60 amps, and they'll pull 3 horsepower and 4 horsepower respectively. And at 716 RPM, that belt can absorb almost 9.5 horsepower. So I've got more horsepower in the belt than I need, and I've got enough speed in the alternators to charge at full or nearly full amperage, even at 716 RPM. So I'm almost finished with my project, at least on the engine side. It's ready to put in the boat, and I got my boating shirt on and I'm ready to go. I hope you've enjoyed this series, and that you are now looking at engine power in a different way and fuel economy in a different way. And you can precisely make changes to those 2 things depending on what you're trying to do. You guys have a good day. If you have any questions, leave comments or send me an email to petehdgs@yahoo. And you guys have a good rest of your life.